Continue with our discussion of quantum devices, and the first quantum device I'm going to tell you about is nothing but the nose. I would like to mention how quantum physics is now combining with biology to give rise to a new field that is called quantum biology. In fact, you must have studied in biology how cell signaling occurs. For example, if you have the cell membrane, and outside the cell membrane is the extracellular environment, there are certain molecules which act like messengers, small molecules that are destructible, that move from one place to another and carry signals. For example, we have adrenaline. Adrenaline is a molecule that gets activated when we are excited. We have dopamine. We have histamine and other kinds of molecules. So these messenger molecules, they are outside the cell environment and they transmit signals between cells, like electrical pulses between cells. Now this information has to get into the cell. So the cell on its membrane has other molecules which are receptors. And the messenger molecule binds to the receptor and triggers the formation of or release of certain proteins. These proteins are called G proteins or cell signaling proteins. The most recent Nobel Prize in chemistry was given to the scientists who discovered and found out the mechanism of the working of these G proteins. So there is a whole mechanism of how signals go from outside to the cell and into the cell. And this G protein, when it gets activated, it acts like a molecular switch. Which is in an off state normally. It's normally in an off state. When the messenger molecule binds with the receptor, it triggers the G protein and the molecular switch is turned on. And when the molecular switch is turned on, ion channels can open inside the cell membrane, which can lead to the transport of sodium, potassium and calcium ions. And if this cell is a neuron, and if it crosses this ion channel, crosses the action threshold or the action potential, the neuron will be triggered. And this electrical impulse will then travel to the brain. So this is how we see, this is how we smell. Now I have a view graph that actually describes this process in a little bit more detail. Amazon laser pointer. So as you can notice here, there are in the epithelium of the nose, in the nasal epithelium, there are ciliary molecules and olfactory receptor cells. So the odorant molecules, the fragrance or the scent that we would like to smell, these molecules trigger these olfactory receptor cells, and the signal is then transmitted through a complex network to the proper region inside the brain. Now this view graph is a better description of how G proteins work. So there is a messenger molecule. In this case I've chosen the example of adrenaline. So this small molecule is traveling in the extracellular environment. This is the cell membrane. It's a phospholipid layer, and inside we have the cell. So the adrenaline molecules bind with a receptor. There are specific receptors for specific molecules. So the molecule adrenaline binds with its receptor. The receptor gets activated. It changes its geometry or its conformation. Now this is the G protein. The G protein is tethered to the cell membrane with these chains, with these branches. Inside the G protein there is a small region that is called GDP, guanosine diphosphate. In its normal native state, this protein is off. It's like a switch. If there is no adrenaline, the receptor is not activated, this protein is off. The switch is off. As soon as the adrenaline binds to the receptor, this G protein gets activated. The switch turns on. This GDP portion of the G protein sheds off. It goes off and is replaced by GTP, which is guanosine triphosphate. Now this GTP molecule or protein, it moves along the cell membrane. Wherever it finds this enzyme, adenylyl cyclase, it results in the production of a large number of these molecules, cyclic AMP. AMP stands for adenosine monophosphate. And when these molecules are released, now notice there is only one adrenaline molecule which is resulting in the production of a large number of cyclic AMP molecules. So this whole process is also acting like an amplifier. A signal comes in, a weak, feeble signal comes in. Once that signal goes into the cell with the help of the G proteins, it gets amplified. The result gets amplified. And these molecules then result in the opening up of ion channels. And if this is a neuronal cell, the action potential is, threshold is surmounted, and the neuron fires. When the neuron fires, it transmits the signal to the brain. So this is the basic chemical pathway of what happens when a particular molecule comes and binds with the receptor. But what happens here? There was currently no explanation of how the process of the odorant molecule or the receptor molecule binding with a messenger molecule binding with the receptor takes place. Now quantum physics has come to the rescue here. It has come to the rescue of biologists, and now we have a fairly good idea of how the sense of smell works, and it works on the basis of quantum mechanical tunneling. And it's a very different kind of tunneling. So suppose we have now I'm just going to draw a view graph of how sense is sensed, how scent is sensed. So this is a receptor molecule, for example. And then you have an odorant molecule, something that you would like to smell. For example, let's choose an ester, right, which has a fruity smell. Let's choose ethyl acetate. So ethyl acetate is So any fragrant molecule comes in to this annular region that is exposed by the receptor. The geometry of the receptor is such that this molecule fits in to the receptor through some lock and key mechanism. So this is a key that opens up a lock. So the geometry is such that the receptor allows the incoming molecule to come and settle inside the receptor region. Now what's going to happen is that an electron from this side of the receptor molecule has to cross this barrier. Here we have G proteins. And these G proteins are linked up with the receptor molecule. Somehow you have to activate this molecular switch. So what happens is that this connection, this tethering connection, has to be opened up, which means the G protein has to be reduced. It has to gain an electron somehow so that this link is severed, this link is broken, and as a result the molecular switch will be triggered on. So this G protein requires an electron from somewhere. Now this region of the receptor molecule has some excess electrons. So these excess electrons have to cross this bridge and go into this region of the receptor. This region of the receptor is called the acceptor region, and this region of the receptor molecule is called the donor region. So what really has to happen is that an electron has to cross this bridge. It has to cross this barrier. Now this is an insulator. Ester, it's an organic molecule. It's slightly polar, but it does not conduct electrons because it does not conduct electricity. So somehow electrons have to cross the barrier. Now how do they cross the barrier? They cross the barrier through tunneling. What happens if I would like to draw an energy level diagram of this whole process? I have a donor region, and inside the donor region the electron is at a certain energy level. I have an acceptor region, and inside the acceptor region any electron that is inside the acceptor region is at some energy, and there is a difference in energy between the donor and the acceptor. So first of all, an electron has to enter the donor region, a free electron which is labile, which can move. So where does this free electron come from? This free electron comes from some other molecules that are present nearby. Excuse me, you're not allowed to use mobile phones. This is something which I need not tell you. So this free electron has to come from somewhere, but everything here is an insulator. So we would require a molecule that is a reservoir of free electrons. And what is such a molecule called which can provide free electrons? What kind of agent is it? It's a reducing agent or no? It's a reducing agent. So we need some kind of reducing molecule, a reducing agent in the vicinity of the cell. And in fact one such agent is already available. It's called NADH. It's a reducing agent. It is a reservoir of electrons. It can supply electrons, and another molecule can gain those electrons and be reduced. Okay, have you come across this molecule? Yes. All right, in chemistry or in biology. So NADH is available. This NADH becomes a reservoir of electrons. These electrons go into the donor region. This energy is E1. Now the electrons have to cross this barrier. This is insulator, this is air, so the electrons cannot readily cross this barrier. So what happens is that the ester molecule comes in, the odorant molecule comes in, and the electrons through the odorant molecule, they tunnel through from the donor region to the acceptor region. So tunneling takes place. The electron falls into the lower energy E2. So why do we need an odorant molecule? Tunneling could have taken place without the presence of the odorant molecule. Can you guess why we need some molecule here? No, but the electron goes from the donor region to the acceptor region. The electron comes here. This electron breaks this bond. It reduces this bond. It's a disulfide bridge. It is reduced. The G protein is released. Can you tell me why do we need an odorant molecule?
Like a conductor.
It doesn't act like a conductor. It's an insulator.
It may just provide a spark, penetration path obstruction.
But electrons can also tunnel through air.
Resistance in air may be higher than
आप बताओ.
The different odorant molecules might have different penetration lengths.
So you need chemical specificity. So different odorant molecules will result in different kinds of penetration lengths.
It blocks out other ions, sodium plus.
Okay, one thing that you notice here is that this energy level is higher than this energy level. So when an electron tunnels across this barrier, what happens to its energy? Its energy goes down. So energy has to be conserved. So where does the excess energy go? The excess energy has to be depleted or exhausted somewhere. So that excess energy goes into the odorant molecule. Okay? So this odorant molecule starts vibrating. Okay? This odorant molecule starts showing oscillations or vibrations. And these vibrations in quantum mechanics, they are called phonons. So this is an example of what is called phonon assisted tunneling. Now what is a phonon? Okay, do you understand why do we need an odorant molecule? We need an odorant molecule because if the electron has to tunnel from the donor region to the acceptor region, its energy goes down by delta E, which is E2 minus E1. So this thrown off energy, this energy that is shed off by the electron has to go somewhere. So that energy appears as the vibration of this odorant molecule. The odorant molecule starts oscillating. Alright? So this oscillation is called a phonon. Now what is a phonon? I would like to take about 5 minutes to discuss what is a phonon. We know what is a photon. What's a photon? It's a packet of energy. What kind of energy is this? It's electromagnetic energy, which travels in the form of an electromagnetic wave. Okay? The photons are massless. So the photon is a quantum of energy. Okay? A phonon is a quantum of vibrational energy. Any molecule that we talk about acts like a harmonic oscillator. And if we have a harmonic oscillator, we know that the potential energy curve looks like a cup-shaped parabola. And all the energy levels of course for the electron or for the vibration of this molecule, they are quantized. So this lower energy level represents the ground state vibration of the molecule. Okay? So this level is n equals 0 level. This is the n equals 1 level. This is the first excited vibrational state of the molecule. If the molecule is at 0 energy, or if the molecule is in its ground state, then it will have some minimum energy, which is the 0 point energy. And what is that energy? It's half h bar omega naught. So the energy here is half h bar omega naught. Do you agree with me on this? So these are the vibrational energy levels of a molecule. The molecule is acting like a harmonic oscillator. What is this omega naught? Which frequency is omega naught? Angular frequency, but what in the context of the vibration of the harmonic oscillator? The frequency of vibration. Which vibration? There are many vibrations. The ground state, first excited state. It's the fundamental frequency. Okay? Which, suppose you have a mass that is attached with the help of a spring. This mass is m and the spring constant is k. Then omega naught squared is just k over m. It's a natural frequency. Okay, you have a pendulum which has a certain length and it's inside a gravitational environment. So there is going to be a natural frequency, which is omega naught square is going to be L over G, right? G over L, right? L is mass, length. This is meter per second square. So it's going to be G over L. So every oscillator has a natural frequency. So the frequency is omega naught, and in a ground state, the vibrational ground state, the energy is half h bar omega naught. What's the energy in the first excited state? It's half plus 1. Okay? It's 3 over 2 h bar omega naught. In the nth state, the energy is n plus half h bar omega naught. So the vibrational energies of a molecule, like the odorant molecule, they are quantized. So if the molecule is in the ground state and you would like, now this represents a molecule in the ground state. This dot does not represent an electron, it represents the molecule that exists in a ground state. Okay? Now if you would like to make this molecule excited, okay, then the molecule has to go to a higher level. But how can you excite this molecule? How can you excite higher vibrational energies? By an incoming photon, for example. The oscillator absorbs a photon and the oscillator gets excited. But another mechanism is just to increase the temperature. If you increase the temperature, it's very possible that this nth level is occupied. Okay? Agreed? So you just increase the temperature and the oscillator goes to an excited state. The amplitude of oscillation starts increasing, which means that the energy has to go up. Quantum mechanics tells us that this energy is quantized. And these discrete energy levels come out of the Schrödinger equation. But you have to solve the Schrödinger equation for a parabolic potential. When the oscillator is in the nth excited state, okay, its energy is n plus half h bar omega naught. Now we define this gap. What's the magnitude of this gap? It's h bar omega naught. we define this gap as a phonon. Okay, this gap is called a phonon. What we can say is that if the oscillator is excited to the nth level, its energy is n plus half h bar omega naught. What we can say is that the oscillator has n plus half phonons. Or we can ignore this half term because generally n is very large, and we can say that this oscillator has n phonons, or n phonons have been excited. Each phonon has an energy h bar omega naught. So we see that n phonons have been excited. Phonon comes from the Greek word which means sound or vibrations. So a phonon is a packet of vibrational energy. It's a quantum of vibrational energy or sound energy or acoustic energy. That's what a phonon really means. So a phonon can then be treated like a particle, just like a photon. Even though it's not a real particle, it's a quasi-particle, it's a virtual particle, but it can be treated as on equal footing with a photon. It acts like a particle. Just like you have energy levels inside a band, and inside these energy levels you have electrons. And one of the electrons is excited, it goes to a higher energy level and it leaves a vacancy in this energy level. So this vacancy is called a hole. Okay? You must have studied this somewhere in A levels or FSC. So this vacancy is a hole. Now a hole is not a real particle because it's just a deficiency of an electron. But it can be treated like a particle. It has a mass. Just like the electron has a mass, it has a charge. Like the electron has a charge. The hole is positively charged. So a hole is not a real particle, it's a quasi-particle or a virtual particle. It can be treated like a particle. And as we know from this course, the distinction between particles and waves is very blurry. So we take this liberty and we are freely calling these particles, these phonons and holes, as particles. So the phonon can act like a particle, and we generally say that the phonon is a particle. So what is happening in phonon assisted tunneling is that an electron moves from a higher energy level to a lower energy level and emits a phonon in the process because energy has to be conserved. So what we have, if you make a diagram of an electron, this is an electron with energy E1. It is converted to another electron with energy E2, and the excess energy goes off as a phonon of the correct energy E2 minus E1. Just like photons can be emitted when an electron makes a transition from a high energy level to a lower energy level, when an electron moves from a higher energy level to a lower energy level through tunneling, a phonon has to be emitted. If the electron moves from a lower energy level to a higher energy level through tunneling, a phonon has to be absorbed. So this process of smelling involves phonon assisted tunneling. But one thing I would also like to mention is this point that I've highlighted is that n is much greater than 1/2, or the ground state energy is very small. Now let's look at a numerical example that can verify this fact. Ji.
So does this happen in atoms too? Phonon is emitted.
If you have an atom inside a solid, and there are many atoms inside the solid, then the atoms of the solid can oscillate. So phonons can be emitted in a solid. You need a matrix or a medium for phonons to exist. And another point, can an electron be created or destroyed? No. An electron cannot be created or destroyed. You can change its energy, but the electron cannot be created or destroyed. But a phonon can be created or destroyed. If you have the oscillator excited to high energy levels, new phonons are created all by themselves. And if you have the temperature go down, the phonons will be annihilated. So phonons are not conserved. They can be created or destroyed through temperature. Now one example I would like to give you about phonons, and another thing that I've only mentioned in the passing, is the Bohr's correspondence principle. Now I'm going to ask you one question at least about this principle in your final exam as well. Suppose we talk about, let's take a very simple example, a miniature example. Let's take a very small object, like an eyelash. ठीक है, एक पलक लेते हैं. ठीक है, so this is an eyelash. And on the tip of this eyelash there is a teardrop. ऑलराइट, कोई आपकी पलकें हैं, उसके ऊपर एक छोटा सा आंसू का टुकड़ा है. ठीक है, कोई पलकों पे चमक रहा है एक छोटा सा मोती. नाउ व्हाट आई वुड लाइक टू नो is that this system is acting like a harmonic oscillator. Now this is quite an anticlimax, because such a beautiful object is being likened to a harmonic oscillator, which is dry and which is dull and boring, but nevertheless the analogy does exist. Suppose this teardrop has a certain mass, say 1 microgram. And this teardrop by its weight is being pulled by gravity downwards. And this this eyelash has a certain spring constant. Suppose the spring constant of this eyelash is 0.1 newtons per meter. Now what I would like you to calculate is how many phonons are excited in this system. Can you perform a calculation of how many phonons are excited in this system? This teardrop is being attracted by gravity. So there is a certain force that this teardrop is exerting. Okay? What you would really like to find is the energy of this system. Right? So can you find the energy of this oscillator? नहीं. H bar Now this is a real test of your knowledge of comprehensive physics. As I mentioned, you cannot make distinctions between mechanics and modern physics and electricity. It's all one organic whole.
So find out the of x and then.
Excellent. And what's the value of n now? How many phonons have been excited? What's that? Minus 10. So how many phonons have been excited? How do you do that? No idea. So treat this as a harmonic oscillator. What you do is, first of all, you find out the natural frequency, omega naught. That's given by k over m under root. And then you would like to find out the total energy of this oscillator. So if this is the downward force acting on the eyelash, the downward force is mg, and you divide this by k, you get the total displacement, x naught. So this eyelash is bent downwards. This displacement is x naught. It's just F over k. Hence the energy is going to be half k x naught squared. And you equate this energy to n plus half h bar omega naught, which you've already calculated. You can find out what the value of n is. So what's n here? Anyone? 2.9 into 10 over 22. It's a huge number of phonons. In other words, such a small system, एक पलक पर एक चमकता हुआ आंसू, such a small system is such a large quantum system. From the perspective of quantum mechanics, it's a very large system because it has been excited to such a high energy level. And if you look at the wave function for this system, for the teardrop, the wave function will have 10 raised to power 22 nodes approximately inside this small length, inside a 1 millimeter. So if I draw the wave function is approximately given like this. And how many nodes are these? There are about 10 raised to power 22 nodes in this much length, in about a millimeter or so. So it's such a highly excited system that the wave nature of quantum mechanics is totally washed away. And what you see, you do not see the wave nature. You see a continuum. This is called the Bohr's correspondence principle. Therefore, even such a small system, a miniature or a microscopic system, is in such a highly excited state as far as quantum mechanics is concerned that you don't observe the quantum behavior. This is called the Bohr's correspondence principle. So if you really want to be Shoulder to shoulder with quantum mechanics, you really have to go to small temperatures in which the phonons excited is very small, or you near the ground state or the first excited state or the second excited state. You need to go to small temperatures, or you need to talk about very small objects, which means you have to reduce X naught. When you reduce X naught, the energy goes down and the number of phonons excited goes down. Alright? So I used a poetic device to actually describe you what phonons are and how they can be treated mathematically, and what is the Bohr's correspondence principle. Now what I would like to tell you about is another very important device, which is the workhorse of modern electronics, and which makes life possible these days, and that is a transistor. And I'm going to approach transistors from a quantum mechanical perspective. But before I talk about transistors, I would like to tell you about something simpler, because we're going to use this concept while we discuss transistors, and that is a capacitance or capacitors. Do you all know what capacitors are? Have you studied capacitors before? Everyone? Knowing something and knowing really about something are two different things. Just knowing the name of something and understanding something, totally different ball game. Suppose I have a capacitor and I have a resistor. Now this is going to be a mathematical a slight mathematical detour, so be careful and be attentive. I have a battery and I have a switch. So this resistor is R and this capacitance is C. Now what I do is, the capacitor is initially uncharged. Okay? So there is no charge on the capacitor. What I do is, I close this switch at time t equals 0. First question, will current flow through the circuit? क्या current flow करेगा circuit में से? Yes. Will it keep on flowing forever? No, it's not going to flow forever. So what's going to happen is that this is the positive terminal of the battery. Current will flow. It's going to make this terminal of the capacitor positively charged. So when this terminal becomes positively charged, this becomes negatively charged. Now this positive charge resists or impedes the flow of current, because current is generally the flow of positive charges, conventional current. So the current that goes into this capacitor decreases with time. Eventually, when the voltage across this capacitor becomes equal to the voltage of the battery, will current stop. Okay? Suppose I close the switch at time t equals 0. What I would like to do, I would like to see how does the charge on the capacitor change with time. Okay? This is something I would like to explore mathematically. So this is a closed circuit. I can apply Kirchhoff's voltage law. This is the voltage V0. This voltage is shared between the capacitor and is dropped across the resistor. So what's the voltage on the capacitor? If C is the capacitance and Q is the charge on the capacitor, what's the voltage? Right. Q over C. And what's the drop across the resistor? I into R. But what is I? Current. It's the current. So how do you define the current in terms of charge? dq by dt. So I have R dq by dt. Now what's this? This is a differential equation. Can you solve this equation for me, please? Have you studied this so far in your differential equations course? No? No or yes? Yes, you have. It's a first order differential equation. Can you please solve it for me? क्या? करंट है ये. इंटीग्रेटिंग फैक्टर की आवाज आई मुझे. So this is my differential equation. I multiply both sides by an integrating factor. ठीक है, ये पढ़ा हुआ ना इस तरह की चीज. Now the left hand side turns out to be the derivative of q times the integrating factor. I integrate both sides, so this is an exact derivative. So when I integrate this left hand side, I just obtain what I differentiate, and the integral of this is r c e t over rc plus some constant a. Okay, so this rc, so there's an r here, sorry. So this r cancels out. I divide both sides by e t over rc. I get q equals v naught c plus a e minus t over rc, where a is some arbitrary constant. Now how do I find this constant? From the initial conditions. At time t equals 0, what is the charge on the capacitor? What's the charge on the capacitor at time 0? 0. So if I have this equation, I put 0 on the left hand side. This becomes CV naught plus A. This term becomes 1. So my A turns out to be minus CV naught. Hence I have found out what the arbitrary constant is using the initial conditions. Now I put this A back into this equation. My charge as a function of time equals CV naught one minus E minus T over RC. Now what is CV naught? What are the dimensions of CV naught? Charge. And what is CV naught? It's the total charge on the capacitor when it is fully charged. When it has been charged up to V naught, the voltage of the battery. Because when the voltage of the battery is V naught and the capacitor is fully charged to the same voltage, the charge that it holds is CV naught. So this is the maximum charge the capacitor can hold if you supply a voltage V naught. So this is some Q naught. Now can you please plot how charge varies with time based upon this expression? It's not linear. Constant. It's exponential. It's not linear. So there's a different kind of shape. It's going to go like this. And this is Q naught. ठीक नहीं है? Wrong. ये ठीक नहीं है ये.
ये टी बढ़ता जाएगा, ये टर्म बढ़ता जाएगा. ये वन को
तो बढ़ता जा रहा है.
ये एसिम्प्टोटिक.
तो चार्ज बढ़ता जा रहा है. तो फिर आगे क्या होगा? आगे दिखाएंगे. रुक जाएगा इधर से आके. What's the charge at time t equals 0? It's 0. So your at time t equals 0, charge should be 0. What's the charge at time t equals to 0? No, at time t equals 0, it's 0. So your graph should start from 0. शाबाश, गुड. ठीक नहीं है. I have a demonstration to show as well. So this is time axis. Time axis and the charge on the capacitor Q of t. At time t equals 0, this term is 1, so the charge on the capacitor is 0. Initially the capacitors are uncharged. So I start off from here. When my time goes to infinity, very large times, this term goes to 0. When this term goes to 0, Q becomes CV naught, which is the maximum possible charge on the capacitor. So if I have CV naught here, I draw a dashed horizontal line. For long times my curve should approach this line asymptotically. So my curve goes like this. So this is a plot of that. This is the charging curve of the capacitor. And this shows that if you have a capacitor and you suddenly apply a voltage to it, that is, you close the switch, the charge on the capacitor does not suddenly go to CV naught. This is wrong. It takes a certain length of time for the charge to build up on the capacitor. Okay? And you can look at this expression at when you have time equal to RC, then this becomes e raised to power minus 1. 1 raised minus e raised to power minus 1 is 0.63. At a time t equals RC, the capacitor charges to 63% of its maximum value. So this RC tells you how long does it take for the capacitor to charge. This has dimensions of time. RC has dimensions of time, and it's called the time constant. Now suppose what happens is that this switch has been closed, okay, and this capacitor has built up all of its charge. So the charge on the capacitor is now CV0, and now you remove the battery. So you have a charged capacitor placed in series with a resistor, you remove the battery, and you have a switch that is open. So you have charged the capacitor. Please be attentive. Can you just write down the differential equation, please? V0 तो यहाँ पे है ही नहीं. डिफरेंशियल इक्वेशन लिखो, और ये भी गलत है. Just write down the differential equation, nothing else. So for the discharging part, there is no voltage, there is no battery. So the drop across this object, the capacitor, which is Q over C plus I into R, the current through the resistor, which is dq over dt into R equals 0 because there is no battery. You just apply the Kirchhoff's voltage law. So dq over dt is equal to minus q over RC. So dq over q is minus dt over RC. And how do you solve this equation? You take the integral of both sides. You take the integral of both sides, you obtain q equals q naught e minus t over RC, where q naught is the initial charge on the capacitor. Again, you use the initial conditions to determine this constant, which is q naught. So this is a discharging curve. So if you initially close the switch, the capacitor charges. Suppose it builds up all of its charge, and then you remove the battery and then close the switch again. The capacitor is going to discharge, and it's going to follow this law when it discharges. Now this is an exponential decay. So the capacitor charges, and during its discharge period, the capacitor exponentially changes it decreases its charge, it gives away its charge. So it does not immediately give away all of its charge, it does not discharge suddenly, rather it takes a certain amount of time to discharge, and that time again is given by the time constant. So now I have a demonstration, a couple of minutes long demonstration that actually shows this behavior for a capacitor. ठीक है? और मैं ये कर रहा हूँ, instead of having a switch and manually opening and closing this switch, I don't manually open and close the switch. What I do instead is I have a capacitor and a resistor, and I apply a voltage that goes off and on, off and on, off and on, off and on. So when it goes off, it's just like opening the switch. Okay? And when it goes on, it's slightly more complicated than that. When it goes on, it's putting a voltage in series with this. So if what I have in front of you, there's no need for the webcam possibly. What I have in front of you is a circuit with a resistor and a capacitor, and I'm going to apply this voltage, this square voltage, up, down with the help of the computer. So my computer is providing the voltage, and the voltage across the capacitor, which is proportional to the charge across the capacitor, I'm also measuring with the help of the computer. So my signals are coming out of the computer and they're going back into the computer with the help of a data acquisition system. Alright? So my computer is acting like a function generator as well as an oscilloscope. Okay? And remember, I'm going to use this description when I discuss transistors on Monday. Alright, so I'm going to apply a voltage of frequency 5 Hz, and this middle, okay, can I somehow refresh this or remove this data that's already there? Okay, that's never mind. Clear out. Alright, so what I have is a frequency of 5 Hz. I am applying a square pulse of frequency 5 Hz, and I have an RC circuit. The pulse is of amplitude 10 volts, so the pulse goes between 0 and 10 volts, 0 and 10 volts. Here is the pulse that I am applying, and here is the voltage across the capacitor, which is going to appear. And this voltage across the capacitor is of course proportional to the charge on the capacitor. And as you will notice, the charge does not suddenly go up and down. It rises exponentially and decays exponentially. And by the way, this will show you the voltage across the resistor. Okay, and probably in the exam I'm going to ask you what's the mathematical form of the voltage across the resistor as well. Anyway, so I'm going to apply this pulse and see what do we get. Alright. So this is the voltage that I have applied, the pulse, on, off, on, off, on, off. So when the voltage is on, the capacitor is charging. So it starts off from 0 volts and it charges to a maximum value. So this rise is exponential. And in fact, we'll perform this experiment in the physics lab next semester as well. This rise is exponential and it follows this curve, this one, functional form. The functional form of this charging region of the capacitor is exponential. When this input voltage goes negative, the capacitor starts to discharge. When the capacitor is discharging, it does not suddenly go down to zero. There is a time constant for it. And we're going to use this time constant as the time in the energy time uncertainty relationship when we discuss transistors. So this discharging is exponential. It goes down, the voltage goes up, the capacitor starts to charge again. And then the capacitor discharges, charges, discharges. And the bottom graph is the voltage across the resistor. So let me now turn down the voltage a little bit, or let me just increase the frequency so that the pulse goes on off at a higher rate. Let's make it 10 Hertz. Right. So here is what you observe. The maximum amplitude is 10 volts. So the capacitor is charged to 10 volts. Let me increase this even further. Let me make this 30 Hertz. Alright, now what you observe is that the pulse is at a higher frequency, at a frequency of 30 Hertz. So it's changing 30 times in a second. But now the capacitor initially stored a charge of 0 coulombs and it had a voltage of 0 volts. Now it's not fully charging up to the 10 volts because this frequency is higher. Before you are intercepting it before it has been fully charged. And when you reverse the direction of the input pulse, the capacitor starts to discharge. So it has not yet fully charged to 10 volts. You intercept it earlier and it starts discharging, and it has not fully discharged. You increase the voltage again and it starts charging again. So this region is exponential e-charging, this region represents exponential discharging. If I reduce the frequency, say I move it to 1 Hertz, this is what I obtain. A slow frequency, the capacitor charges, and as you can notice, it charges to its maximum value in about 50 milliseconds. So 5 times the time constant is 5 times RC is about 50 milliseconds. You can determine with the help of how long does it take to charge fully, you can determine either the resistor or the capacitor and the product of the resistance and the capacitor. So it has fully charged and then it remains constant. You cannot put more charge onto the capacitor, it's saturated. And then when you close the switch, the capacitor starts to discharge. And it discharges with a certain time constant. It does not suddenly go to zero. If the capacitance is higher, this curve will be fatter. It will take longer time to discharge. Capacitance is smaller, it will quickly discharge. In the third graph, this is the voltage across the resistor. The voltage across the resistor is I times R. It's R times the derivative of charge. Now charge is proportional to the voltage across the capacitor. So if you take this graph, can you tell me what the relationship between graph number 2 and graph number 3 is? What does it look like? Not opposite, it's something else, something deeper. G? Can you tell me mathematically the relationship between the third graph and the second graph? Opposite, negative, something else. Shabash. Slope. If you take the slope of this graph, you get this graph. So this third graph is the derivative of the first graph. इससे जाहिर होता है कि डेरिवेटिव और इंटीग्रल सिर्फ मैथ की और ब्लैक बोर्ड पे नहीं होता, ये आपको नजर आता है. These are physical phenomena. You take the second graph and its derivative is the third graph because this is Q. You take the derivative of Q, you get dQ by dt, which is the current through the capacitor and the resistor, and the voltage across the resistor is proportional to the current through the resistor. So this third graph is a derivative of the second graph. देखो यहाँ derivative is suddenly changes to positive and its slope is decreasing. So the slope is decreasing. When this voltage remains constant, the slope becomes 0. Now the slope suddenly it becomes negative. So there's a downward spike here. And then the slope steadily becomes positive, 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 which means the slope is in the upward direction, and then you get the slope 0 because the voltage does not change. So this is a description of how a capacitor charges and discharges In the next lecture on Monday, which starts at 9 a.m., we'll see what happens when a quantum dot is charged and discharged, and how does that lead to single electron transistor.